my goal for today is to wrap up damping. We got squeeze, film damping, and then lateral damping to cover, and then talking about how in real MEMS devices, it's usually multiple damping mechanisms. Then we are going to move along to pressure sensors, which is a pretty short topic. So I think we can cover all of that today. At least that's the goal. We'll see. So when we finished up on Wednesday, because today is totally Friday, we had come up with a relationship for the spring constant and the damping coefficient for a solid plate in a squeeze film damping situation. Now we're going to talk about what happens when our plate has perforations in it. Okay, so this is going to attempt to be a side view here of a portion of a plate where we have our substrate on bottom, and then we have our plate up here on top. Like so. Move this one out a little bit so that all of these things are the same size. So this structure up here with the vertical channels in it is representative of a plate with holes in it, where our plate has some thickness H, and it is a nominal distance D away from our substrate. So when our plate moves down, what's going to happen is that the air is going to get squeezed out from underneath the plate, much like we saw with traditional squeeze film damping, but there are now additional escape paths for the air to go to, right? So some of it's going to go over this way, some of it will go this way, and then we'll see air escape through the hole, and we'll have something similar for all of these perforations through our plate. So on the right-hand side here, I am going to attempt to draw a portion of a top view, okay? So bear with me, as you all know that I can't draw circles to save my life. So for the math that's involved in how this behaves, we look at our plate as a connected system of cells, where each of these dashed circles represents one cell, and interior at the center of each cell is our actual hole that is the path through which our air will escape. Okay, so each of these cells has a particular radius, RC, and then each of these holes has a particular radius measured from the center to the outer edge that we're going to call R naught. So RC is our cell radius, and R naught is our hole radius. Okay, so the purpose of these holes is to not allow the air to compress by giving it more pathways to escape through. So we should not have a spring constant for these situations, because the entire purpose is to not allow for compression, right? We are going to have a damping coefficient, and our damping coefficient to some extent is going to depend on the thickness of the plate. If the plate is very thin, the air that's passing through the plate will not encounter any large amounts of flow resistance through that channel. And so we'll have one particular damping coefficient, If the height of the plate or the thickness of the plate is very large, we should see that the flow resistance of those individual channels dominates the damping. And so we're going to have a particular damping coefficient for that particular configuration. Okay. So let me write down here, this was a top view. So for thin plates, and so I'm going to call a thin plate, the thickness is on the order of the hole radius, not, they don't have to be exactly the same or anything like that, but just not particularly thick. Flow resists through the holes and be neglected. Yielding a damping coefficient of gamma gas is equal to 3 times the effective viscosity times the cell radius squared over twice our gap distance cubed times this parameter. Excuse me, cubed. It should be cubed. I wrote squared. Thank you for catching that. This factor is multiplied by n times pi RC squared. This is nothing more than our effective plate area, the number of holes times the area of each cell, all added together. And then this expression is in turn multiplied by 4 times R naught over RC quantity squared minus R naught over RC to the 4th power minus 4 natural log R naught over RC minus 3. That is correct. Yes, I will make a point to note that. Yeah, I actually, you can see here, started to do a derivation, scrapped it out, and was just like, no, they're not going to want to see that. It's just going to get gross. Yeah. So for thick plates, where H is much greater than R naught, the damping coefficient is gamma gas is equal to 8 pi n mu effective times RC to the 4th power times H divided by R naught to the 4th. And if this seems too easy, it is. We actually have to modify our effective viscosity equation in this regime. Where mu effective is going to be, this is a big fraction, R naught times the square root of pi over 2 times the mean free path times the viscosity at standard atmospheric pressure divided by R naught over the square root of pi over 2 times the mean free path plus 5.94 times 1.78 times that quantity R naught root pi over 2 mean free path plus 1 divided by 2.625 times that same R naught times root pi over twice the mean free path. Plus 1. So we have 2 different damping coefficients for very thin plates and then with perforations, and then thicker plates with perforations. And then the damping coefficient for plates with no perforations is larger than all of these, right? So for a thin plate, it should be the smallest it's going to be for this particular situation. For a thick plate, it's going to be a little bit larger because of the flow resistance. And then when there is no perforations, the damping constant will be at its largest for squeeze film damping. Okay, and I will have you guys show that in a homework problem. All right, so our last, well, topic if we're going to throw any math at least for damping, is lateral damping. So I am again going to draw a terrible picture. We have our plate like so. Down here, we have our substrate, which is obviously stationary, and say that our plate is moving to the right with some velocity v. What's going to happen is that we are going to see that air gets dragged along with the plate due to shear flow between the plate and the substrate. So we're going to have a profile something like this. I'm trying to draw as effectively a straight line like that, representing the shear flow of the air. Okay. Because the plate is moving parallel to the substrate, the effects of squeeze film damping are effectively 0, and we only have shear flow. So for a plate with area A and gap D, where this is our gap dimension, we have a lateral damping coefficient, gamma lat, is equal to mu effective A over D. Looks suspiciously like the equation for a parallel plate capacitor, where mu effective in this situation is the standard viscosity over a factor of 1 plus twice our Knudsen number. Okay. This particular model neglects the effect of the mass of the air that is being moved, as well as air drag on the top and the sides of the plate. So it's only considering that bottom surface contributing to this lateral damping. All right, so these are 2 forms of damping that there is some math, arguably annoying math, but math associated with it, right? For a true understanding of the damping coefficient of a microstructure, it's likely going to require the use of computer simulation tools, because in most cases, there's not just a single form of this type of damping. Let me explain what I mean by that. So I'm going to draw a picture here where we have substrate, and then we have fingers. Or a capacitive cone drive. So let's say that this finger is fixed, this finger is fixed, and this finger in the middle is movable. So what kind of damping would we expect to see? Yeah. So movable, the direction of movement, let me do it in a different color so that we don't get too confusing. And this horizontal direction. So, Stephen, you have a.
I was gonna say you should be lateral damping on the part underneath, and then we can on the one that's moving forward, since here's.
Exactly right. Yeah. So there's going to be lateral damping. So let's say that it's moving to the left. So we're going to have lateral damping in this region. I'm going to put some dots around it. Let's call this region 1. Then you correctly identified that there's going to be squeeze film damping here as air gets squeezed out as the movable finger gets moved towards the stationary finger. So let's call that region 2. But then we also have this part right here, which is a transition between shear and lateral damping and squeeze film damping. We have this region up here where we're transitioning from squeeze film damping into free space. Yeah, that's pretty much it. So for a simple structure like ones that we have analyzed multiple times in this class at this point, we actually have multiple different components of just the air damping. And then we also have to take into account transfer of energy into the anchor losses, any surface roughness that we encounter, the intrinsic damping of the material itself, all of those things. So 99% of the time, you're going to wind up just using computer simulations to look at everything as a whole and look for that total damping coefficient for a structure like this. So you'd use COMSOL, ANSYS, or some other sort of multi-physics thing to get a total picture of what's going on to figure out what the damping effects are. All right, so I think we have talked enough about damping, so let's talk about what I believe to be a much easier topic, and that is pressure sensors. So pressure sensors rely on being able to measure the difference in pressure across the faces of a membrane. Okay, so in its most simple form, we might have some sort of structure like this. So this would be an example of kind of a surface micro machined thing. So here we have a first wafer. Here is our second wafer that's been fused on top, such that there is a, what I call this, space. What's a fancy word for space? There we go. Here's a vacancy. Thank you. Where we have some pressure P1, right? Between these two dashed lines, so this thing down here, we have a flexural membrane or diaphragm. And so if there is some different pressure P2, then that differential pressure P2 minus P1 is going to cause that membrane to deform. And a pressure sensor is literally just a device like this, where there is some sort of transducer integrated into it to measure that deflection in some way and convert it into an electrical signal, right? So that could be putting piezo resistors at the locations of maximum stress and then measuring that stress as our membrane deflects to generate some output voltage. It could be using a capacitive system to where there's a very thin insulator here, so that effectively the distance between the diaphragm and the substrate changes, which results in a change in capacitance and therefore a change in our output voltage for our measurement circuit. So those are the two principal ways that pressure sensors are realized. So in order to quantify those changes in membrane deflection, we need to understand how and why a membrane deflects due to pressure. So now we're going to hit you guys with a whole bunch of equations again. Okay. So let's start with something simple-ish. Circular mechanical membranes. So attempting to draw a circle here. I am intentionally using dashed lines because what's inside of the circle here represents our membrane. And what's outside here represents our support structure. So for this circular membrane, let's say that it has some radius A, and in a coordinate system, really the only thing that we're going to be concerning ourselves with is the radial distance R away from that center point. Okay, so this is kind of a top view. And then for a side view, we'd have something like this. We have our support structure. So this distance from here to here is the diameter of our circular membrane. So it has a diameter of 2A. Our membrane has some height H. And when we have some pressure P acting on the membrane, where this P represents a differential pressure between the top and bottom surfaces, we should expect to see some deflection W that depends on the radial distance R. So this is our side view. And now let's hit you guys with the math. Okay. So W as a function of R is given by 3 times 1 minus the Poisson's ratio squared times PA to the 4th power over 16 EH cubed. That term there is multiplied by a factor of 1 minus R squared over A squared quantity squared. And underneath here, I'm just going to define things just so we're all making sure we're talking about the same thing. V is Poisson's ratio, which is a material dependent constant. P is a differential pressure. A is the membrane radius. E is Young's modulus. H is the membrane thickness. And R is the radial distance away from the center of our membrane. So common sense tells us, and the math bears this out as well, if my stylus will write, that the maximum deflection will occur where? At the center, right? So maximum deflection is simply W evaluated at 0, which is just that first term, right? 3 times 1 minus Poisson's ratio squared, PA to the 4th power over 16 EH cubed. Okay. So our diaphragm surface will undergo both radial, so that would be our normal stress, and a transverse stress. Okay. So radial stress, TR as a function of radial distance, is given by plus or minus 3/8 times PA squared over H squared. This is multiplied by 3 plus Poisson's ratio R squared over A squared minus 1 plus Poisson's ratio. So that is our radial stress. Where do you think it's going to be at its maximum? At the boundaries, exactly right. So where the anchor is effectively for this structure, just like we saw in a cantilever spring and all that kind of stuff, the maximum stress occurs at the anchored boundary. Okay. So the radial stress will be at its maximum, TR max at TR at A. And this becomes plus or minus 3/4 PA squared over H squared. And just for your inquiring minds, the positive is for tensile and the negative is for compressive stress. So effectively, On the top surface, you'll wind up having a plus sign here, and the bottom surface will wind up having a negative sign, assuming deflection is up. We can do a similar treatment for the transverse stress. So T sub T as a function of R. That same plus or minus 3/8 PA squared over H squared. And now we're going to have 3 nu plus 1, or 3 Poisson's ratio plus 1 times R squared over A squared minus 1 plus nu. The maximum transverse stress also occurs at the boundary of our diaphragm. So TT max is TT evaluated at A, comes out to be plus or minus 3/4 PA squared over H squared times nu, which is exactly what we should expect, because that's the purpose of the Poisson's ratio, is to convert stresses in different directions. Okay. Last thing here is the stress at the diaphragm center. So at the center of the diaphragm, the radial stress and the transverse stress are equal. And it's going to be minus plus 3/8 PA squared over H squared times 1 plus nu. So we should see that the top surface is in compression while the bottom surface is in tension if we're pushing up. So those are the governing equations for a circular membrane. Now we're going to talk about a square membrane, and I want to be clear here that everything here is an approximation because the math is horrifying. I was originally going to do rectangular membranes as well, and then I just said no. So square mechanical membranes. So I'm going to first give myself a coordinate system here. So this will be our Y direction. And this will be our X direction. And let's say that this dashed line here represents the boundary of our membrane, so that the total length here is twice A. And total length in this direction is also twice A. So this is our top view. Our side view is going to be very similar to what we saw for our circular membrane. Really, the only difference is that our deflection is going to be measured as a function of position in a Cartesian coordinate system, right? So this distance is once again twice A. Our thickness of our diaphragm is H. if we have some differential pressure acting on our membrane, we observe a deflection W that is a function of X and Y. And this is our side view. All right, so going to follow a similar treatment. Membrane deflection, sorry, getting ahead of myself. So our membrane deflection at some point XY will be approximately W as a function of X and Y. Will be 12 times 1 minus nu squared PA to the 4th power over 47 EH cubed. Times 1 minus X squared over A squared, quantity squared, times 1 minus Y squared over A squared, quantity squared. Once again, we should see that our maximum deflection occurs at the center. So that's just 12 times 1 minus nu squared PA to the 4th over 47 EH cubed. So we are going to have normal stresses in the X and Y directions, and then our transverse stress will simply be our normal stress multiplied by our Poisson's ratio. Too many L's in that normal. That is a good joke. So in our X direction, as a function of X and Y, we're going to have plus or minus 24 over 47 PA squared over H squared times 1 minus Y squared over A squared times 1 minus 3X squared over A squared plus nu times 1 minus X squared over A squared times 1 minus 3Y squared over A squared. And for our normal stress in the Y direction, it's going to be literally the exact same equation, except we swap all of our X's and Y's. So 1 minus X squared over A squared times 1 minus 3Y squared over A squared plus nu 1 minus Y squared over A squared 1 minus 3X squared over A squared. So where is maximum stress going to occur for the square membrane? It's the center of each of the spans. That's absolutely, yeah. So the locations of maximum stress will be here, 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 and here. Okay. So the maximum normal stress, Tn max, and I'm not going to give you the specific coordinates because there are 4 of them and they're equal, and we've identified them on the figure, but it's, 0, A, 0, negative A, A0, and negative A0, will be approximately plus or minus 48 over 47 times PA squared over H squared, and the maximum transverse stress is literally just Poisson's ratio times our maximum normal stress. So that same plus or minus 48 over 47, PA squared over H squared times nu. Okay. At the center of the diaphragm, our normal stress in the X direction and our normal stress in the Y direction will be equal to each other. We'll have a value of plus or minus 24 over 47 times 1 plus nu. Actually, PA squared over H squared times 1 plus nu, just so that it's in the same form as everything else I've done. So, Stephen, sorry for making you get out your whiteout dealio. So, all right. So like I said, we're not going to do rectangular membranes because the math is just absolutely horrifying. They do behave pretty similar to square membranes. So we're also not going to do any mathematical work with a capacitive pressure sensor because once again, the math is horrifying because we have a non-parallel plate capacitance. So it's going to involve, for small deflections, a double integral and the use of a Taylor series expansion. And it gets worse if the deflection is larger. So we're going to look at piezo resistors because the math is not horrifying there. Okay. So non-parallel plate capacitor, yeah, the membrane is one of your plates. So when the membrane deflects, so just as a graphical thing here to show why we're not going to do the math, right? So the substrate down here, that's one plate. And then you have your deflected membrane exaggerated here, which is the other plate. Because the gap isn't uniform, we can't use epsilon A over D anymore. We effectively, so if this were just a curved plate, it wouldn't be that bad because we could slice this curved plate up into small sections, each of which have a specific gap, and they're all electrically connected in parallel. So we would just add them together in one dimension and it would be okay. But now we have a ton of infinitesimal area plates that we have to integrate over both directions, and the math just gets ridiculous. So I don't want to do it, so I'm not going to do it. So instead, let's look at a piezo resistance system. Okay, so let's say that we have a plate like so. So these are the boundaries of my plate. This distance is 1 millimeter because it's a square plate. This distance is also 1 millimeter. This will be our X direction. This will be our Y direction. And just throwing a coordinate system on here. So hopefully a fairly obvious question, but if we were going to develop or design a piezo resistive pressure sensor, where would we want to put our piezo resistors? Exactly right. The locations of maximum stress, because maximum stress is going to give us our largest change in resistance. I know it's been a while since we've looked at piezo resistive things, so the fractional change in resistance is the longitudinal piezo resistive coefficient times the longitudinal stress plus the the transverse piezo resistive coefficient times transverse stress. So to see the largest possible change in resistance, we want our stress to be as large as possible. So let's start by looking at a system where we have longitudinal piezo resistors at the edges of our diaphragm so that they are subjected to maximum stress, and they're oriented in such a way that the normal stress is the longitudinal stress, so that our change in resistance, let's call this change in resistance in the X direction, is going to be pi L times T normal max plus pi T times T transverse max, all times the nominal resistance. Okay. If our membrane is made of 110 single crystalline silicon, that means that our Young's modulus, which I don't think we actually need, is 170 gigapascal. Our Poisson's ratio is 0.06. Our longitudinal piezoresistive coefficient, that was very loud, is 71.8. 71.8 times 10 to the negative 11 per pascal. And our transverse piezoresistive coefficient is negative 66.3 times 10 to the negative 11 per pascal. Okay. And what I'm going to do now also is I'm going to put two more piezo resistors here. Let's do these in gray. Okay. And I'll put one over here and one over here. So they are outside of the diaphragm. The reason they're outside of the diaphragm is so that they do not undergo any stress, so that their resistance value is effectively fixed. If I have 4 resistors, I can then utilize a Wheatstone bridge configuration where I'll have something like this. Exactly right. Yep. Canceled out. So I've got my 5-volt source, and then I have this resistance here, which is just going to be R0. So this is one of our off membrane reference. Over here, we're going to have R0 plus this delta Rx that we're going to figure out what that is in a moment. Here's an R0 down here. Here's an R0 plus delta R here. There's our ground. Here's the polarity of our output voltage that we're going to be measuring. So we could call this node B1 and this node B2, right? So let's say that we are our membrane here is experiencing a differential pressure of 50 kilopascals. I want us to figure out what the output voltage is going to be. Fairly straightforward kind of question here, tying together what we've talked about today with some of the sensing techniques that we've talked about previously, right? I've literally already given us the equation to calculate the change in resistance. So that's fairly straightforward. And then we would simply need to figure out an equation that gives us our output voltage as a function of that change in resistance, which isn't particularly difficult either. So let's start with this guy right here, right? So delta Rx is our piezoelectric coefficient in the longitudinal direction times our maximum normal stress plus our piezoelectric coefficient in the transverse direction times Poisson's ratio times our maximum normal stress times our nominal resistance of R naught, which I don't know that I gave you, so let's call it 10 kiloohms, just so that we have some frame of reference here, right? So if we use the relationship that Tn max is 48 over 47 PA squared over H squared, where I didn't give you H either. I'm not paying nearly enough attention. 2A is 1 millimeter and H was 10 microns. We would find out that our change in resistance here is positive 865.813 ohms. And this corresponds to an output voltage of 207.472 millivolts, where I got this value simply using voltage divider relationships for both sides and then taking the difference of it. Okay. So 50 kilopascals of pressure difference gives us an output voltage of about 0.2 volts. That is absolutely a measurable signal, okay? What could we do to improve upon this design? Exactly right. So increase the sensitivity of the design, meaning that we would get a larger voltage output for the same change in pressure or differential pressure. So making our resistors longer is going to change R naught. And then we're also running into the problem that the longer that our resistors are, they're not seeing the maximum stress, because stress is a function of position. So if we make them too long, we can't really accurately make the assumption that they're experiencing a uniform stress that is the maximum stress over their entire length. Okay. So this isn't an obvious thing, but notice here that our piezo resistive coefficients are of opposite sign. That's pretty much true always, okay? So what you could do to make a better pressure sensor would be to integrate, instead of using a reference piezo resistor pair, have another piezo resistive pair oriented in a transverse direction at your other locations of maximum stress, right? So what you'd find is that you have some delta Ry that is going to be pi L times T transverse max plus pi T times T normal max times R naught. So literally the same stresses that we calculated previously, but now they've swapped piezoelectric coefficients. And you'd wind up getting a negative resistance change, 791.387 ohms in the Y direction, right? How that would modify our measurement circuit is we'd have plus RY here and plus delta RY here. So that one resistor is getting larger, the other resistor is getting smaller. And so you're going to see that the voltage on both sides of the ratiometric sensing is a little bit bigger. Combined together, we wind up getting an output voltage of 412.764 millivolts. Not quite twice as large because our change in resistance isn't identical because our piezo resistive coefficients aren't identical but of opposite sides. Okay. So this is means you're using the exact same number of resistors, but because you have creatively put the second pair of resistors in a place to where they experience a negative resistive change, the overall output voltage tends to increase.
Will the accuracy go down marginally? If we didn't have something extra.
Why? So the temperature sensitivity is going to still go away because we're using a double-ended ratiometric sensing. So any temperature-based effects are still going to cancel each other out to the first order because of our Wheatstone bridge, actually because of the voltage divider situation. And then the Wheatstone bridge configuration also eliminates something else that I can't remember because it's been 6 weeks since I talked about it. But there is a specific reason for using Wheatstone bridges for piezo resistive sensing because it got rid of temperature effects and then wasn't power supply ripple, I don't think. But anyway, it's in a previous video.
I think it was about, it's something about stability of the.
Yeah.
Also on this DC component.
So it eliminates the DC component. We do get. So I'm trying to remember because the overall resistance of this thing from a noise perspective is just going to look like one single resistor having a value of R naught, whereas using single-ended ratiometric sensing, you get half that noise because those two R naughts look like they're in parallel. Yeah, it's in a previous video. Go watch it if you're interested, because I can't remember and my notes are down the hall. All right, so it's 12:13, so we are done for the day and we are done with pressure sensors. So our last topic for this class is going to be gyroscopes, which I believe will take me 2 full days to do. It will definitely take me 1 full lecture and then a portion of the second one. So my goal over the weekend, as I said previously, is to get homework assignments and all that kind of stuff uploaded for you. I'm also going to work on getting a series of questions, much like I did for the first test, to have you guys study for or whatever that'll show up on your second test. I'll also get all the videos up. Yes, so your second in-class test will be Friday. I'm saying this to the people on Zoom, unless you are Jack Weir, who has made previous arrangements with me, I expect to see you in class to take your exam next Friday.